Welcome to Thermal Physics Practical Mastery. Today, we're diving straight into the 0625 high marks strategy.
Okay, look closely at this calculation. Seriously, I want you to put it on trial in your mind right now. The student, they used the perfectly correct equation, they substituted the numbers exactly right. The arithmetic is absolutely spotless. And yet, this exact calculation scored 0 marks in an actual Cambridge exam. 0! Ordinary revision, just memorizing formulas and plugging in numbers, it is completely failing you when the pressure's on. So let's look at the evidence and figure out exactly what went wrong.
The reality is, you're probably not failing because you don't get the physics. You're bleeding critical grade boundaries because of these specific, painful little errors. Missing units on your final answer. Rounding your numbers way too early in a multi-step calculation, which just completely throws off your final value. Giving these vague, kind of everyday explanations instead of rigorous scientific ones. Making silly graph axis errors, like swapping your independent and dependent variables. Using the wrong variables entirely, or, and this is the worst one, writing conclusions that simply are not supported by the raw data sitting literally right in front of you. Time is ticking in that exam hall, right? So how do we absolutely bulletproof your answers against these traps?
That brings us to part 1, the ultimate answer framework. If you want to lock down maximum method marks every single time, you've got to internalize this foolproof 4-step framework. Think of it like building your legal case for the examiner. Step 1, always state the underlying physics concept. Step 2, extract the exact evidence or data directly from the question or the table. Step 3, apply your scientific reasoning to connect that raw evidence right back to the concept. And finally, step 4, use precise examiner wording. Look, mark schemes are hunting for specific keywords. If you walk through these 4 steps, you leave 0 room for interpretation. You are handing the examiner exactly what they want on a silver platter. Let's anchor this framework with a super quick win. We'll define a core Cambridge syllabus concept that comes up all the time: specific heat capacity. It's defined as the energy required per unit mass to raise the temperature of a substance by 1 degree Celsius. Now, notice the extreme precision here. Per unit mass, 1 degree Celsius, every single word earns its keep. You can't just say, oh, it's the energy to heat something up. No way. You need that step 4 examiner wording. All right, let's take this disciplined thinking and actually apply it to some raw experimental evidence.
Okay, take a look at this classic Cambridge-style cooling curve dataset. Notice the time in seconds on the left running from 0 to 300. On the right, the temperature in degrees Celsius is steadily dropping from 80.0 down to 45.0. But hey, scan that right column carefully for a second. If you look at the trend, hiding right there in plain sight is one clear anomalous reading. It's a number that briefly spikes up or drops way too fast before returning to the trend. Extracting this exact kind of evidence, spotting data that just doesn't fit, that is exactly step 2 of our framework.
But wait, in just a moment, I'm going to reveal the hidden examiner clue in this exact data that changes your entire answer completely. Seriously, if you skip applying the framework, just knowing the definition of specific heat capacity will absolutely not save you from this trap. So stick with me.
All right, part 2, the cooling curve challenge. Let's step into the examiner's shoes for a second. Here is a highly flawed learner response explaining that cooling curve data we just saw. They wrote, the temperature went down fast at the start and then slower later because it was cooling. Ouch. I mean, to a complete novice, sure, it sounds logical. Yes, it was cooling. But come on, it lacks any scientific reasoning, cites absolutely 0 evidence from the table, and uses incredibly vague language. This right here, this is exactly how easy marks just vanish into thin air. Now let's bring out the brutal red pen. On the left, we've got our vague, flawed answer. But on the right, look at this highly precise top band answer. This one actually substitutes real values from the table. It says between 0 and 60 seconds, the temperature dropped by 15 degrees, whereas between 240 and 300 seconds, it only dropped by 3 degrees. Boom, that is step 2, evidence. Then it adds, the rate of thermal energy transfer decreases as the temperature gradient between the substance and the surroundings decreases. And there it is, that hits steps 3 and 4 perfectly. Correct units, substituted values, and exam-safe wording. This is how you guarantee your grade. And if you don't do this, 0 marks. Seriously, 0. That is the harsh, totally uncompromising reality of the mark scheme. If you calculate the specific latent heat perfectly, but you, say, forget to include your units, or maybe you round off to one significant figure halfway through the calculation, you get 0 for the final answer mark. Even if you completely understand the physics conceptually, the examiner cannot and will not award you the marks if the final execution is sloppy. So the absolutely crucial point here is ensuring you systematically lock in your marks before you even think about moving on to the next question. You need this rapid-fire examiner checklist burned into your brain. Every single time you finish a calculation or draw a graph, ask yourself, are units present on my final answer? Are my significant figures actually reasonable and consistent with the raw data? If I drew a graph, is the scale correct, covering at least half the page? And most importantly, does the specific numerical data I just calculated actually support my written conclusion?
Which brings us to part 3, the locked door of data analysis skills.
Because here's the thing, calculating the answer perfectly is really only half the battle. As the examiner notes, a strong conclusion means nothing if you cannot evaluate the practical investigation's weaknesses. You've got the framework to write the conclusion now, sure, but you currently lack the skill to suggest top-band practical improvements. What happens when you are asked how to fix the heat loss in this experiment?
The evidence is crystal clear. Without evaluation skills, your perfect calculation is still guilty of dropping marks. So how exactly do you spot invisible thermal heat loss before the examiner does? Well, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Watch the top band evaluation framework explainer next, and let's secure those final marks together.